All right, hello and welcome back to the IB Maths Doctor channel. We are on to a new unit today. It's our first unit of integral calculus, and we're going to begin with a section on antiderivatives and integration. Okay, we're going to talk about what integration is and how it's related to derivatives. This image on the screen will give you a little bit of an idea. Compared to derivatives, we are going to be putting our brains into reverse to essentially undo some derivatives, or as the process is known, integrate, just finding antiderivatives in this sense. Okay? So we'll get right into it here on the IB Math ANA SL syllabus. We're looking at sections 5.5 and 5.10. We've got a lot to cover today. We're going to look at the basics of anti-differentiation. That's also going to be known as integration. We're going to look at integration of essentially polynomials and a bunch of other functions we've seen as well, such as trig functions, exponential functions, some basic rational functions as well. And we'll also look at this thing called integration with a boundary condition and a constant term. Okay? But let's get right into it here, looking at this question. Okay, given a derivative, how do we recover the original function that it came from? Okay, so this is a common starting problem for us, and we want to think about being given a derivative, an f primed of x, and we want to try and find out what function might that have come from. Okay? So if you think about this for a minute or two, you can kind of start getting the idea of what antiderivatives are. You're putting your brain into reverse gear to try and figure out what was the function before the derivative happened. Okay, so you know the derivative with the power rule, you kind of multiply that power in front and then decrease the power by 1. We want to do the opposite here. Okay, and if you play around with this a little bit, it's pretty easy to see that the original function that it came from must have been, what would it be, 3x to the power 4. And you can test this by simply taking the derivative. Okay, so if you take the derivative of this function using your simple power rule, it's pretty easy to see you get out 12x cubed, meaning this f of x was the original function that gave that derivative. Okay, so we just kind of trialed and errored our way through that, but essentially we've performed our first piece of integration here. Integration is just the name of the process that finds antiderivatives. Okay? Now, an important thing we're going to learn here is that the antiderivative is not unique. Okay, so that f of x function we just found, 3x to the 4, that's not the only function that has that derivative highlighted in blue. There's actually an infinite number of functions that have that derivative. Okay, and it will be any function that is 3x to the 4 plus some kind of constant. So it could be 3x to the 4 plus 4. It could be 3x to the 4 minus 1,000, okay? And we see that we won't be able to tie down what that constant at the end of the function is unless we have more information, which is where that boundary condition we mentioned earlier on is going to come in, okay? But we'll see more of that later. Okay? So this leads us to our antiderivatives theorem, okay? We say that this function big f of x, this is the antiderivative of little f of x, okay? All that means is that f primed of f of x, big F of x, is little f of x. That is all it means to be an antiderivative, okay? The derivative of big F of x is little f of x. Okay? All this theorem is going to say is the most general antiderivative of our function little f of x will be big F of x plus some constant c. Okay, so this c is just some constant with no variable attached to it. Okay, and why is that so? Well, we know that the derivative of a constant from our previous unit is always 0. So if we take the derivative of f of x plus c, we're just going to get f primed of x. Okay, and we'll think a little bit about that graphically here. Okay, so we can think about a graph of our function. Our function was f of x equals 3x to the power 4, okay? And we can bring in a calculator to graph that accurately if we like, okay? And we'll do that right here, 3x to the power 4, okay? Let me get my calculator, here we go, 3x to the power 4. Kind of looks like a flattened out parabola. We can go ahead and draw that on our paper. So just sketching here, we're not trying to be super accurate. Okay, so this is 3x to the power 4, and if I go ahead and graph 3x to the power 4 plus that 4 from earlier, okay, 3x to the power 4 plus the 4, all that's going to do is move this function up vertically. Okay, if I subtract from it, so 3x to the power 4, let's say minus 8, I won't go as crazy as minus 1,000, we can just see that it's going to move that function down on our vertical y-axis. Okay? So we get the idea of what this constant is doing. This constant at the back is simply translating our function vertically, which is clearly not going to change the slope or change our derivative here. So it's easy to see that all of these functions that we've written over here would all have the same derivative. All three of those things that are highlighted, they all have the derivative 12x cubed. Okay, so that's what this constant at the back of our function is doing. It's just moving it vertically. So let's carry on understanding a little more about antiderivatives and integration and how they fit together. Okay? So we're going to make a little flow diagram here. We're going to think about a function, we'll call it g of x. Okay? And we know that this function g of x can have a derivative, which we commonly note g primed of x. Okay? And the process of getting from g of x to g primed of x, we've studied that a lot. That is called differentiating. Okay, or finding a derivative. Okay, so that was something we did in units 5 and 6 of this course. We worked on that process of going down from g to g primed of x. Okay? The next two units that we're on currently, unit 7 and unit 8, that will work on the other side of this diagram, which is coming up from g primed to g of x. So this green arrow, how do we get up there? That process is called finding an antiderivative, or it can also be referred to as integrating, okay, or integration. Okay? So we will look at multiple ways to integrate and what that does for us in units 7 and 8. Okay, so this is just giving us a visual of where we are in our calculus journey. We've done the red side of this diagram. Now we're going to work on the green side, that kind of going up element right there. Okay? So let's think back to derivatives. The first thing we learned when we learned derivatives was this thing called the power rule. So our goal here is to find an equivalent version of that, but for integration. Okay, so we'll think first about derivatives, and then we'll kind of derive for ourselves the integration version of that power rule. Okay? So we think about our power rule as having some input, x to the n, and it's basically a machine that has two steps to it. So there's two steps to this machine, and then it spits out an output. Okay? So in words, we remember that taking the derivative using the power rule, okay, we multiply the coefficient by the exponent. Okay? That was the first step of our machine, multiply that coefficient with the exponent. Okay? And then we decrease the exponent by 1. Okay, so we subtract 1 from the exponent. I like to use the word decrease. You'll see why in a minute. Okay, so if we do this, we will get out of our machine n times x to the n minus 1, and that's our common power rule that's in our formula booklet. Okay? So the goal here is to come up with a similar machine that works for integration. Okay, so essentially we want to undo the operations of our derivative power rule. Okay? So what's that going to look like? We're still going to feed in the same input, x to the n. It's still going to have two steps. We'll draw these in kind of bubbles to make sure they're pretty clearly different. Okay? It's going to do two steps, and it's going to spit out an output. Okay? Now, what are those two steps? We need to basically reverse the operations of our derivative power rule. Okay? So going backwards through this derivative machine, okay, we see that this is the thing we need to undo first, decreasing the exponent by 1. Okay? So to undo that, the first step of our integration machine, okay, will simply be to increase the exponent by 1. Okay? And now you can see why I like the words increase and decrease. Okay? I like decrease to go with derivatives to help my brain make that connection. Derivatives decrease, and increase goes with integration, so integrals increase. Okay? So first step will be increase the exponent by 1. Okay? The next step will be to undo the multiply coefficient by exponent. The opposite of multiplication is division. So in this case, we will divide the coefficient by, I'm going to call it the new exponent. Okay, I like that word new in there because that reminds me that I need to change the exponent first with that increase by 1. Okay, so this is our reverse power rule machine, and what will come out of here is x to the n plus 1. That's me increasing the exponent, and then I will divide this by the new exponent, which will be n plus 1. Okay? And I can do this for any exponent I like, apart from one number. There is one exponent I cannot do this for. I cannot do it for an exponent of -1, because if I increase -1, it will go back to 0, and then I'll end up dividing by 0. Okay? And we'll see how we handle that in a minute. So we're going to use that reverse power rule a lot today as we get familiar with integration and antiderivatives. Okay? Before we can do that, we need to understand the notation for integrals. Okay, and it starts with this kind of unusual mathematical symbol, which is simply an integral sign. Okay, this one is typed out and looks perfect, but you can draw your integral signs kind of like this little double hook thing. Okay, they can be somewhat vertical. They can go kind of diagonally backwards. You'll see both variations of this. The only thing we don't want is one that kind of curves back on itself. Okay, this is not a good integral sign because it can kind of look like an S or some kind of musical note. Okay, so either of the first two are fine. The second one we don't really like. Okay? Think of this like an open parenthesis for your integration. Okay, so after your integral sign will go your function that you want to integrate. This has a technical name. Okay, this is called the integrand. That's the thing you are going to integrate. Okay, and then finally you have this dx at the back of your integral. Okay? And this is simply the variable of integration. Okay? This doesn't play a huge role in the standard level course. You might learn more about it when you get to college and take Calculus 1 or Calculus 2, where you get to multivariable calculus. But essentially, this is telling you the variable which is going to act independently, and that's the one you're going to need to actually integrate or apply that reverse power rule to. Okay? For now, we can kind of think of it as just kind of closing our integral. So the integral sign opens like an open parenthesis, and the dx closes our integral like a closed parenthesis. Okay? And how do we communicate this verbally? It's very simple. We just say integral of f of x. We can say with respect to x. That's what the dx is telling us. Or we can just literally read it as it says. We can just read it as dx if we prefer, for this last part right here. Okay? So integral of f of x dx or integral of f of x with respect to x is the same communication. Okay? All right, that's a lot of theory. Let's get in and start actually doing some integrals here. Okay? So integral problems don't need any instructions. The instructions can be given in the symbols. Okay? So we see the integral sign here, and we're being told to integrate 4x cubed dx. Okay? So we're going to apply that reverse power rule, that integral machine, that power rule in reverse. Okay? We're going to go 4x, and we're going to increase the exponent by 1, so that 3 will turn into a 4. And then we're going to divide by our new power, which is a 4. Okay? And notice, when we do this, when we do our integration, when we increase that power, both the integral sign and the dx drop away. So the same way when we did derivatives, we could put that prime on to denote that the derivative has happened. In this case, when the integral happens, we're going to know that because the integral sign disappears as well as the dx. Okay? Well, we can simplify this down. We can make it x to the 4, and we need to add that constant on the end, the plus c, because we don't have any extra information to know if there ever was a constant at the back there. Okay? So think of this like a general solution where it always has this arbitrary plus c on the end. Okay? Now, you're probably going to forget that plus c a lot, and that's okay, but we'll do lots of practice to try and train our brains to remember there's always that constant. Okay, so our second example here is the integral of 8 cube root t dt. So we've changed the variable of integration a little bit to t, and we see that denoted with the dt at the back as well. Okay? We cannot integrate this as it stands. We need to take a little prep step, and that prep step is simply turning this cube root into a power. So we know that that's a power 1/3, and now we can apply our reverse power rule. So we'll increase that power to 4/3. 1/3 plus 1 is 4/3. And then we're going to divide by that 4/3. Okay? Now this is a little double fraction action, which is kind of messy, so we'll go through and clean this up by turning it into multiplication. Okay? So we will have 3/4 times 8 t to the 4/3, which we can simplify to 3 times 8 is 24. That is 6 t to the 4/3, and we'll throw our arbitrary constant, our plus c, on the end there to complete that integral. Okay? All right, next problem is a reciprocal function. So we've got -3 over x cubed, okay? And we will go ahead and attack that by rewriting it as the integral of -3 x to the -3 using our negative exponent work. Okay? We'll apply our reverse power rule. So -3, increase it by 1, it will go to -2. We'll divide by that new power of -2. And then we'll simplify this down to 3 over 2x squared, throwing our arbitrary constant on at the back to complete the integral. Okay? And you can add the c at any stage. I usually add it at the end, but you can add it right when the integral gets done as well, and you'll just carry it with you along through the problem. Okay? Fourth question is a little different. In this question, we're given a derivative and asked to find the original function y. So we can write down that y is equal to the integral of 9x squared dx, showing that knowledge that we know integration is simply the process of finding an antiderivative. And now we can apply our reverse power rule. So this is 9x cubed over 3, which should give us 3x cubed. Again, bring that plus c constant in at this time. Okay? And that's the basics of integration. Okay, now in the IB formula booklet, we are given a bunch of standard integrals, which should kind of get familiar to us as we do more problems. Okay? The first one is exactly what we've been using. Okay, it's the integral of x to the n. This is what we've been calling reverse power rule. Okay, and we said earlier this is good as long as the exponent is not -1. Okay, well, if the exponent is -1, that means we are starting with the integral of x to the -1, which is the integral of 1 over x. Okay, we're actually given in the formula booklet here the integral of 1 over x. We're told that's natural log of absolute value of x, which tracks with our previous work that the derivative of ln x is 1 over x. Okay, so think of this kind of like a patch where we've got a problem with the reverse power rule, and this result will come in and patch that issue nicely. Okay? After that, we get two trig integrals. Okay, so we're told that the integral of sine x is negative cosine x. Watch out for that negative. That's going to trip you up if you forget it and make your problem harder. And then finally, the integral of cosine x is sine x, obviously with the plus c's. Okay? And finally, we have our natural growth integral. So the integral of e to the x is simply e to the x plus c, which makes sense because the derivative of e to the x is e to the x. Okay? So if e to the x has not become your favorite function by now, I don't know what else I need to do to convince you. It's a function that has its own derivative, but also its own integral. That gets us to two straightforward integration rules, not given in the formula booklet. Okay, these are simply sum and difference formulas for integrals. So the integral of two functions added or subtracted together, so f of x plus or minus g of x inside your integral. There is a rule which says you can integrate these functions separately and then add or subtract those two results. Okay, so this is essentially similar to a distributive property for integrals. The second rule is the integral of a constant times a function. Okay? In this case, you can bring that constant outside your integral and simply integrate just the function of x. So this works kind of like factoring out constant multiples. Okay? What do these two rules do? They allow us to integrate big, long strings or big, long additions and subtractions of whatever function we like. Okay? So we can integrate 3x to the power 4 minus 8x to the negative 4/3 plus e to the x plus 3 cosine x plus 2 dx all in one line here. Okay? We just go term by term. So we go 3x to the 5, increase that exponent by 1, divide by the new exponent, minus 8x to the negative 1/3, that's coming from negative 4/3 plus 1, and then we'll divide by that negative 1/3, we'll clean that up in a minute. The integral of e to the x just stays e to the x. The integral of 3 cosine x, the integral of cosine is sine x, so that will go to 3 sine x. And finally, this last bit is kind of tricky until we really understand it. The integral of 2. Okay, a lot of people mess this up and they say, oh, it's 0. That's because they've still got their derivative head on. Okay, we want to ask the question, what function has a derivative of 2? Okay? And the function that has a derivative of 2 is simply 2x. Okay? So when you integrate, you can think about these constants regaining their variables or regaining their x's in a sense. Okay? And finally, we'll add our plus c on the end. But before we finish this, we should probably kind of clean this problem up and get rid of some of that messy algebra. Okay? So it won't simplify too much. It'll go 3x to the 5, okay, plus, okay, this will be 24 over x to the 1/3 if you do the algebra with that negative exponent work, plus the e to the x, plus the 3 sine x, plus the 2x, plus our arbitrary constant c. Okay, and that'll work for that antiderivative right there. Okay. Moving on to a little more IB style problems. Okay, here we're asked to write this expression with t's in that form t to the p minus 3t to the q, where t and p are ez. This is the symbol for integers, so those should be integer powers, okay? And hence find an integral. Okay? So this is an IB style problem where we begin with some algebra. The easiest way to tackle this algebra is to think about uncommon denominatoring this problem. So right now it has a common denominator. We can split it into two fractions to reduce each of those separately by basically making the denominator separate. Okay? So that will give us t cubed over t5, which is t to the negative 2, minus 3, and we can even call this t to the 0 if we like. Okay? And this is now in the form they want, so p is equal to negative 2, q is equal to 0. Those are both integers. It said it wanted us to find them, and we found them. Now, the IB connection comes in the command terms for part B, which are hence and find. So hence is telling us we should link it to the previous problem. The link we want to make, we don't want to integrate what they give us. We want to integrate what we just simplified it to. Okay? So we want to integrate t to the negative 2 minus 3 times t to the 0 instead of that fraction they gave us. Okay? Applying our reverse power rule, this is t to the negative 1 over negative 1. Minus 3t to the 1 over 1. We can clean this up and simplify it to 1 over t with a negative in front, minus 3t plus our arbitrary constant c. Okay. So what we've done in this problem is take a quotient and use some algebra manipulation to turn it into a reverse power rule integral. Okay. And at this point and all through Unit 7, okay, we're not going to have any rules for either products, quotients, or composites. Okay, so when we were doing derivatives, we had a product rule, a quotient rule, and even a chain rule by the end. For integrals, we're not going to get to that stage at any point. Okay, so we just have this reverse power rule and these couple of standard integrals given to us to work with at this point. Okay. All right, the final thing in this set of notes is this idea of finding the equation of a curve when we have this thing called a boundary condition. Okay, so a general equation that comes out of an indefinite integral when we integrate f of x, okay, let me call this f primed of x, okay, we get out our original function f of x and we still have this plus c. Okay, so this plus c is unknown, which leads us to refer to this as just a general equation. It's not specific. We don't know what the c is. Okay, how do we find the c? We have to have a little more information. Okay? And that little more information is simply a known point on the curve, and that will allow us to find this value of C. Okay? This is what the IB refers to, this extra information. This is what they call a boundary condition. Okay? So that boundary condition will allow you to go from a general equation to a specific equation or a particular equation. Okay? Good news is it's a little more work, but it's pretty easy marks from the IB. Okay? So we're given in this problem the gradient dy dx is 3x squared minus 8x plus 5, and we're told that the curve passes through this point 1, negative 4. Okay? So this 1, negative 4, this is our boundary condition. This is what we're going to use to find the C towards the end of the problem. Okay? Question asks us to find the equation of the curve, so we're looking for y equals. That's going to be our unknown here. Okay? So we can find y by simply integrating the derivative, taking the antiderivative if you like. Okay? So we can set up a nice integral here, the integral of 3x squared minus 8x plus 5 dx. We can apply our reverse power rule. So that's 3x cubed over 3 minus 8x squared over 2 plus that 5 will regain its x, so it will go back to 5x plus the c. Okay, now before we substitute in our boundary condition, we want to simplify this equation down to make less calculations and less algebra for ourselves. Okay. Now we can substitute in that known point, so negative 4 equals 1 cubed minus 4 times 1 squared plus 5 times 1 plus c. We'll crunch the numbers here. This is negative 4 equals 1 minus 4 plus 5 plus c. And we can get this down to give us c equals, what have we got there? I believe that is, the negative 4's cancel. 1 plus 5 is 6. C should equal negative 6. I think I'm missing something. We'll go with c equals negative 6. Okay? Don't forget to answer the question. The question asks for the equation of the curve. So that is x cubed minus 4x squared plus 5x minus 6 for our final answer right there. Okay. All right, the bottom of this page has one more optional example. This is a great time to pause the video and try and answer this question yourself. I'll write down an answer in a second so you can check your work. But if you want to try out your integration techniques with a boundary condition, pause right here and then unpause when you're ready for the solution. So the solution to this problem is y equals x cubed over 3 plus x minus 7 coming from the boundary condition and finding that constant c. Okay? You can have this in an equivalent form such as 1/3 x cubed, but anything similar to that is going to be considered correct. All right, we wrap this part of the video with one more IB style problem from a paper 1 that's going to involve some trig functions. Okay? So we're told here the function f of x has a local maximum at x equals pi over 6. So if we interpret that into derivatives, that means that f prime of pi over 6 has to equal 0. Okay? Thinking back to our previous units, that's what happens at a local maximum. Okay? Part A tells us given the first derivative, we need to find the value of d. So if we apply what we just wrote down, f prime of pi over 6, that means negative 2 sine pi over 6 plus d should equal 0. Okay? We've got a one variable equation we can solve here. D equals 2 sine pi over 6. If we need to find sine of pi over 6, we can go back to our unit circle work. Pi over 6 is a 30-degree triangle. So our 30, 60, 90 is 1 root 3, 2. And then because we want sine, that's opposite over hypotenuse. So that will be 1/2. So sine pi over 6 is 1/2. Substituting that in, we find this d value is a nice clean integer of 1. Okay? In part B, we're told that the original function f of x passes through this point pi over 3, 6. And we're asked to find what that function was. So this is where we need to use the integration we just learned. We know that f of x is the integral of negative 2 sine x plus our d value of 1. Okay, if we do this integral, the integral of sine is negative cosine. So this will be negative 2 times negative cosine x plus the integral of 1, which is just x, plus that arbitrary constant c. Okay? And you should be able to make the connection here that this is pretty similar to the previous problems we've done where we're now expected to find this boundary condition. Okay? We were given a point in the question, that was the pi over 3 6. That should allow us to find this constant c. Okay? So 6 equals 2 times cosine pi over 3 plus pi over 3 plus c. Cosine of pi over 3 is a 60-degree angle. So in our 60-degree triangle, we have those sides, root 3, 1, 2. We want cosine of pi over 3, so that's adjacent over our hypotenuse. That is a half as well. So 2 times a half plus pi over 3 plus c. A little bit of math simplifying gives us this c value of 5 minus pi over 3. Okay? That's not the nicest, cleanest constant in the world, but it doesn't need to be, because all we need to do is put it at the back of our function here. So our function is 2 cosine x plus 5 minus pi over 3. And if you like, you can even hold it together in a parenthesis just to drive home that idea that it's really just a single number. All right, final part of this question asks us to find the x-coordinate of the point of inflection. Okay, so we know the definition of a point of inflection is going to be where the second derivative is equal to 0. Okay, so we already have the first derivative. We're just going to go ahead and find the second derivative. Okay? So f double prime of x, that will be the derivative of negative 2 sine x plus 1. So your second derivative will be negative 2 cosine x plus 0. And because we're looking for an inflection point, we set that equal to 0. So we are essentially solving cosine x equals 0. Okay? We want the first positive inflection point. So how do we solve this? That's more unit circle work. We are looking for places on the unit circle where the x-coordinate is 0. Okay? That would be right up here at the top of the unit circle. X is the angle, which in radians here for us is simply pi over 2, or in degrees, 90 degrees. They just wanted the x-coordinate, so that's what we can find right there. Okay? So this is supposed to mimic the IB-style problems where they love to mix derivatives with integrals, and you're bouncing around between the two different strands of calculus. Okay? Recalling things that you might not have done for weeks, such as inflection points and the properties of local maximums and local minimum. Okay? So this is the basics of integration and antiderivatives. Hopefully you found this video useful. In the next part, we will move on to section 7.2, where we start looking at ways to approximate area. Thank you guys for watching. If you found this useful, give it a like, give us a subscribe, and we'll continue our journey through IB, ANA, SL calculus.